Welcome. I want to talk about energy and connectivity in networks. If a network is more connected, then it also has more internal energy. So if you're losing up some connection, you're losing also some internal energy. It's very intuitive, and there are mathematical theorems about this. A very well-known result is that if you have a graph and you look at the Kirchhoff Laplacian, which is the zero form Laplacian, and you look at the eigenvalues, then if you are looking at the subgraph, then the energies are becoming smaller. And that's universally smaller or equal. It's universally true. Here's an example of a star graph. It's an example of a star graph, and we have a complete graph. Everything is connected with each other, and this is a subgraph of this, and the eigenvalues in this case are clearly smaller than the eigenvalues here. The largest eigenvalue, the spectral radius, is the same. So this can be quantified in various ways. For example, you can look at the average eigenvalue. That's also a measure for energy, and this is by the trace formula. This is the sum of the diagonal elements, which is just the 2 times by the Euler handshake formula, the 2 times the number of edges. So if the number of edges grow, also this average number of eigenvalues grows. And also another indication is if you take the product of the non-zero eigenvalues, this is the divide by n, the number of vertices, then you get the number of trees, spanning trees in the network. This is in the case of the complete network that Cayley has already known that here in this case there are 5 times 5 times 5 times 5 divided by 5 is 5 to the 325 trees in this, spanning trees in this network. There are much less spanning trees here, right? So in this case there is actually just one spanning tree because this is just the tree itself. So that's another indication. You can also look at the number of forests, and number of forests, that's by the Chebotarev-Shami's theorem. You have a nice formula in terms of the product of 1 plus I, so it's not, this is always positive here, so you don't have to look at the pseudo-determinant. It's in general true. There's a result I talked about last year, and it's a generalizing result of Anderson and Morley have estimated the spectral radius like this using the vertex degrees, and I in general prove this for arbitrary eigenvalues. This is an upper bound for the eigenvalues of a Kirchhoff Laplacian. Pretty cool result, but it also shows that higher connectivity is really also, correlated with higher energy. Then, of course, you can ask yourself what happens with the higher order Laplacians, like the first form Laplacian, which is in electromagnetism, which is prominent there. The Maxwell equations you can write as L1 of u is equal to 0. So the harmonic forms of the one form Laplacian, so the harmonic forms are the photons, are the particles. So that's why I think about ground state energies as particles, because in the one form Laplacian, in the context of electromagnetism, the Maxwell equations are equivalent to the fact that you have, harmonic forms are solution, wave equations. Then you can look at, is this principle true for the higher order Laplacians? And the answer is no, not in general. Here is an example. You see kind of a network, which is a sub-network of that. In this case, you have just one ground state. There's just the Betti number is 1, the genus is 1, and here the genus is 2. You have 2 holes. So in this case, the dimension of the kernel is 2. So there are 2 ground states here. So there are more ground states here than here. So you would expect that the energy is getting bigger, right? But here actually there is one eigenvalue which has been positive here. These are the eigenvalues you can write down, sinus square pi k over n. So this is explicit eigenvalues here you can write down. Also here the eigenvalues you can actually, in this case 8, you can write it down explicitly using square root of 2 or square root of 3. It's not true that the eigenvalues here have become bigger. even though it's more connected. More connected means more energy. So if you have higher energy, you would expect that, you know, the Betti numbers actually decrease, but here the Betti numbers have increased. So it's not true, and you can look also in higher Laplacians, it's not true in general. So this is kind of just for the higher order Laplacian, this is just a rule of thumb. And of course I was thinking about this in the context of this fusion inequality, which actually has here a much more connected graph. So there's an open set and a closed set, and you fuse them together, and this is much more connected than the separated thing. So you have a Laplacian for the separated system, and you have a Laplacian for the fused system, and of course you would expect that the fused system has larger energy, so less zero eigenvalues, and so that's what you expect here. So that's what this equality means. It means that there are no particles, no additional particles have been created if you just join the system together. So in the laboratory, if you just look at the system itself, at the closed set itself, and the neighborhood, and then the energy has, you expect the energy to be smaller, so you expect to have more zero eigenvalues. And this happens, I mean, these are examples. So in this case, it's actually equality, it's not an inequality, right? You have an open set, which is just one interval, right? So one edge alone. Of course, the Betti vector is 0, 1. You can write down the Hodge Laplacian, it's a zero matrix. The 1 times 1 zero matrix, so which has a kernel, one-dimensional kernel in the form-Laplacian. So this is explicit here in this case. This is, you know, a line graph, a linear graph. It's contractible, so it's 1, 0. This is a circular graph, which is 1, 1. So here it adds up nicely. Here we have seen, I've mentioned that a couple of times already now. In this case, you have actually, in this case, you have less, right? So it actually is a strict equality. So there is a 1 form and a 0 form have collided and become annihilated, and there is only the 0 form which is left. Also here, this is an example, right, where you have a 2 form and a 1 form have collided. So what happens is this is a strict equality. This is an example of the example I started with, an open disk and a closed disk. You put it together, you get the sphere, and the sphere, of course, has Betti vector 1, 0, 1. There's a 2 form by work-related duality, and the 0 form. There's no 1 form because there's simply connected. So this is 1, 0, 1. That's a 2 sphere. This is a contractible 1, 0, 0, and this has a 2 form there, which cannot be, you know, it's not exact because there is nothing at the boundary. So these are examples which kind of, you know, for this inequality, and of course I was trying to prove this using this energy principle. So that's what the energy principle would expect you to have, but it's false. So in general it's false, and maybe I just show you kind of an example here. Let me actually just see here. This is so what I have here. I have Mathematica. I run that. I take a random graph and actually see. In this case, I just take the difference between the energy values. I'm looking at this difference here between the energy values, but for the form-Laplacian, in this case, when we have one system is connected and one system is not connected. So let's just see. Run it again. So in this case, we actually were lucky. The energy principle was actually true. Here it's false, so we have already an example. See, you have sometimes to try a little bit. So in this case, the energy has, some of the eigenvalues have actually become smaller when you join it. So that would, in principle, you would then, if that can happen, you would think that there might be some eigenvalue which becomes 0. There is a nice trick which does the job, and I think it's actually kind of working. When you take here the Witten coordinates. Witten coordinates are obtained by deforming the exterior derivative. The exterior derivative deformation does not give this is isospectral here, but this is not isospectral. Already the Dirac operator is not isospectral. So the eigenvalues change of the form Laplacian. That's kind of what happens. And but it allows you to massage the situation so that the energy inequality works. And what I do is just I take the G. The G is an arbitrary function on the complex, and what I take is I just take the G equal to 1 at the interface where two of the things are coming together and 0 else. So I'm kind of putting the microscope at that point, at this point, and in this case I'm actually seeing the thing. And one can then use, like the Hadamard variation formula is the idea. You have the eigenvectors also, kind of you can control the eigenvectors also, and then you can see with the Hadamard variation formula what happens, right? The lambda prime is equal to u L prime u, where L prime is the change. You make the deformation, and this only changes on the interface part, and this is a unit eigenvector here. And the unit eigenvectors are getting deformed with the Witten Laplacian. Let me just show you that. I'm actually looking at the interface parts. The interface part is actually just the simplices which are involved in the in the merger. And then I'm looking at here. So what happens here, the difference at 0, and then I'm looking at, you see what happens is actually when I'm deforming the thing, what happens in, that's kind of when the Witten parameter S becomes bigger and bigger and bigger. So what happens here, we get monotonicity. So the idea is just to deform the situation here to here, using a straight line connection, and you just look what happens with the eigenvalues in this microscope, when you look at this microscope. And then the energy principle holds. You can have not gained another 0 eigenvalue in any k form, so it should be then hold for this Betti vectors. But it's nothing written down, and I have to see whether this really works. But I'm pretty confident this is very robust, looks very robust. That's it for today.